good?
Good.
Many thanks. So, but to get there, we have to talk a little bit more about negation. Maybe review some things, but certainly talk about some new ones. So, first off, let's talk about not P implies Q. So, let's say I have this statement, if something, then something else. And I want the opposite of that. Like, what is the negation of that? And this is a very tricky thing to think about unless we think about the switch thing that I talked about. So let's just review how those switches, that switch idea works. So I've got a switch here, and that was P, and then I've got a light bulb over here, and that was Q. So P closed, switch on means true, switch off, it's in a false state currently. Light bulb on is true, light bulb off is false. So let's think about that truth table as well. So we had P, Q, and then we have P implies Q. Maybe you can help me out here. Thinking about this, and this is like, is this a legitimate, is this possible? If the switch is off, the light bulb's off. That sounds totally cool, right? That could happen. So that's a true situation. What about if the light is off, the switch is off, but the light is on? Could that happen? Yeah, Tracy, do you remember how the reasoning, you're right, it's true. Do you remember the reasoning for why that still could be true?
You said some like outside like input or something?
Yeah, there might be some other switch, right? So there could potentially be some other switch, you know, like P prime or something that turns this thing on. So yeah, very nice. What about this one though? My switch is closed and the light is off. No, that can't. If this is the legit setup and this is a power source, when that switch is on, that light is on. So this is a false output. It can't happen. And then, of course, if the switch is on and the light is on, that does make sense. That's why we put the switch there. So what is the opposite of this? Well, to say that this thing isn't true, so basically, so not P implies Q is the state where this thing is actually false. So this will be true. This is true. How about this? It's true when P implies Q is false. And P implies Q is false means that the switch is on and Q, the light is off. So the opposite of P implies Q is this. The switch is on, but the light is off. So and, not Q. Switch on, light off. And that's how I would negate this statement here. So let's do a little practice here. If it is raining, we'll start off with words, then the pavement is wet. Pavement, how do I spell that? Pavement is wet. What's the negation of that? What's the sentence that is the negation of that?
If it is not raining, then the pavement is not wet.
So it's not gonna, so it seems like that would be the case, but check this out, Abraham. The negation of an if-then is actually not an if-then, and that's a weird thing. Oh, yes, Sophia, yeah.
If it is raining, then the pavement is not wet.
So no if-thens, let's say it without if-then.
Oh, it is raining, the pavement is not wet.
And the pavement is not
And
wet,
the pavement.
that's it. So check this out, yeah, thank you. So, and it's tricky, because you would think it's a conditional, but it's not. So the negation of this is, it is raining, and we have to avoid those if-thens, which is so tricky, and the pavement is not wet. That sounds suspicious. I keep trying to not say sus. I say it because I watch Tic Tac, and Tic Tac, oh my God, like how freaking old am I? Like really old. But on TikTok, I was just seeing sus all the time, and I started saying it at home. My wife's like, "Really?" Okay,
You meant to put it as not raining?
thank you. Thank you, Trace. Because we want not that and
Not
wait, whoa. No, I do want it is raining.
okay.
Okay.
It is raining.
You have mind control powers over me. I do what you say. So it is raining and the pavement is not wet. That's totally cool. Yeah, so my wife started saying stuff. She's like, "No cap." She's just like, "Oh yeah." I'm like,
Oh, that would be so funny.
It's pretty sad. Okay, cool. So, how about this one? If n squared is even, then n is even. What's the negation of that? So we use the formula, right? We've got the formula here. And how about this? We make it a little bit more fill in the blanky kind of thing.
I know the answer.
Yeah, Joey.
Okay, it is n squared is even and n is not even.
Yeah, that's lovely. And what does it mean to not be even?
It means it's odd.
Yeah,
Or
awesome.
or not an integer.
Yeah, exactly. I should have been a little more precise, so you're right on all accounts there. But this is our negation here. So keep in mind then that a negation is not an implication. On that exam, do you remember that actually the truth table, one of the truth tables, in the very first page, we had this. We had P implies Q, and do a truth table for that. And then we also had not P or Q. Does this sound vaguely familiar from that exam? You'll have to get it back in a bit. But these have the same truth table. So these are identical. So I just want to kind of like explain how this is even possible. To say this is the same thing as this, which is weird, because this is that whole switch thing. But you could also say this same, you can give the same intent by saying not P or Q. So what if I negate this? So let's take not this, not P or Q. What rule do I use to do not of an or statement? Yeah. Whose law? It's a law. It's like one of the De Morgan's, yeah. So I can use De Morgan's law on this. So by De Morgan, this is going to be, you want to help me do it, Sophia, or feel like you've done a lot already?
All I got is the and.
Okay, cool, that's right. So the or, I love that. The or turns to and I just take not this and not this.
Okay.
So it's going to be not P and not Q. So I'm just taking the not of those. What is not? It's just the positive, right? Yeah, exactly. So it's just P and not Q. So just a little bit of motivation as to why this actually works. Using De Morgan's laws, we can show that the negation of this is actually just this. So. Cool. All right. We're going to use that in a bit to do some stuff. Here's a couple other things we didn't get to talk about earlier. So let me remind you, what is this? You can help me. What does this mean? Shaking our old memories awake. How do I read that? Trayson's got the right idea. He doesn't know, he's looking it up. What? Universal quantifier, yeah, awesome. So how do you read that then? That's beautiful.
Everything.
Yeah, for all. Yeah, nice, we got it. It's all there. We have these things in us. Just have to awaken them, release the kraken. And so, I'm not talking about that dumb kraken thing, Joey. You got me thinking about politics. No, I don't want to go there. Sorry, I shouldn't have gone there. So this is for all x, universal quantifier. What about this one?
There exists.
There exists, yeah. That's the existential quantifier, and that's there exists. So this is existential. Oh my God, existential. There we go, holy smokes. Existential quantifier, and it is there exists. So I want to negate these things, and I want to do it with a better pen. This pen is a little faded. That's a little bit better. So here's the negation over here. If I want to negate a statement that's saying for all, how about this? We say for all x something is true. So when I read this statement, I would read this as for all or for every x, p of x is true. That's the way we're going to encounter it. What is the opposite of that? Can you even think it through? So like, can we think this through? What would it mean to say this is a lie? How would you prove it was a lie? Everyone in here has 3 quarters in their pocket. For all students in our class, for all peoples, me too, everyone has 3 quarters in their pocket. How do you disprove that?
You open everyone's pocket.
What was that?
And not all people.
Not all people, yeah, so what do I need to disprove that statement? Like,
Isn't it like EX, not PX?
yeah, but let's just think, like, come back to just the scenario. You're like getting really abstract and going out there. Yeah, Kyle, yeah.
You just find one person who doesn't have 3/4.
That's it, right? So that, I was looking for something a little bit more down to earth, and you were doing like the highfalutin logic. So if I want to disprove, for everyone in here has 3 quarters in their pocket, like Kyle said, I just need to find one person that doesn't. And that would be me, because I only have this weird ass gold coin I found on the street today. I don't know what it is. I'm gonna pass this around, but I want it back. Somebody tell me what that thing is. It's a doubloon. Yeah, have you ever seen a coin like that? You have?
Yeah. I mean, is that a dollar?
Yeah.
Is it a dollar?
Yeah.
Why is it gold?
It's a golden dollar. I found one at Red Rocks like a couple weeks ago. I was super lucky.
Yeah.
That's $1?
Uh-huh.
Okay, give me it back, now we know. We'll make this like a prize or something in here someday, that'll be a prize. Not today.
Golden doubloon.
So, to disprove, to say that this is false, all I need is one that says this is false. So the opposite of this is there exists an x such that not p of x. So let's write the sentence out. There is some x for which not p is true, i.e. p is false. So here's all I want you to get out of that. To negate for all, it becomes there exists. So that's the key thing here for that. So not for all is equivalent to there exists one. Then let's do the opposite. So, if I have there exists some x such that p of x is true. Notice how I'm saying such that? That's like hidden in here. And I would read that way. So there is some x that makes p of x true. So that's the way I would read that sentence. What would be the opposite of that? What would be the opposite to say, there is someone in here with 3 quarters in their pocket? How do I prove that one? Or what's the opposite of it? There is someone in here with 3 quarters in their pocket. What's the opposite?
There isn't.
There isn't, yeah. Can we use some like this language up here for all there exists?
There's everyone that doesn't have 3 quarters in their
Yeah, no one has any quarters in their pocket, right? So for all people in this class, there are no quarters in their pocket. So that's what I'm trying to get at, is the negation of there is something is that there is nothing anywhere. So the opposite, the negation, is for all x, not p of x. Let's write out what that is. For every x, not p of x is true, i.e. p of x is false. It's tricky. Is a question? Are you pondering this? Or?
No, I'm just no, we're not.
Okay, cool, all right. Alrighty, so let's put some of this stuff together. Your turn. Please negate each one of these. So find the negation. And write it as a sentence, please. Let's practice. Negation. Negation. Alright, so there is an integer n such that 2n is prime. What is the negation of that? And so I'm going to put 3 of them up here, so let's just take some time. For every integer n, if n is divisible by 4, this one's they're getting trickier as we move down the line, by 4, then n is even. So you've got a bunch to negate here. In this one, you got to negate the first part, and the quantifier, and then the actual statement. And then number 3, last one, is there is an integer n such that, that's st is such that, n squared is even, and n is odd. You might need a special logic rule to negate that one. So let's write it. So there's a quantifier in front, negate that, and then negate the statement itself. And just do the best you can. Maybe it's just like even thinking through what would be the opposite of this. Take a moment, we'll touch base. Okay. Will you let me know, just like, you don't have to tell me anything private or anything, just like, is she okay? That's all I'm really worried about.
Yeah, that's what we're all trying to find out.
Yeah, okay. Anybody help me out on the first one?
No?
For every integer n to a u is not prime.
Yeah, that was supposed to be an N, but I can see why you think
Oh.
it's a U. Yeah, that's beautiful. Yes, absolutely, yeah. Sorry, that did look like a U. But, so Drayson took there exists an N to turn it to for all or for every, for all integers N. Notice it's still an integer. It's just the for all and the there exists that swap places. 2n is not prime. Beautiful. And that's just the simple negation. This is a simple statement. 2n is prime. What's the opposite? 2n isn't prime. That's all. Can somebody help me out on the second one?
There's an integer where n is divisible by 4 and n is odd.
Beautiful. Yeah. So see how that works? We've got, so Yvonne took the first part for every integer n, converted it to there is some, and we could even, you can add some words in here. There is some integer n to make it seem easier on the ears and the mind, and such that, notice how this such that comes with every there exist. Like that phrase is what makes it actually like a sentence. Otherwise, you'd like talking like math cave person talk. There is some integer n such that, and then Yvonne negated an implication. N is divisible by 4 implies n is even. So this is P and this is Q, and so this and not this is the negation, such that n is divisible by 4, and n is not even, and Yvonne went the extra step and said n is odd, which is lovely. Can someone else help me with the third one? Daniela, you got that third one? No, it's okay. All right, cool. Tracy looks like he has it, but we're making do double duty here. Abraham, what do you think?
For every integer n, such that n2 is odd and n is even.
Cool, so let's start off. What was your first thing? So you said for all integers n, so good for a start. So for all integers n, we're gonna leave out the such that because that doesn't go with the for all. That's like stays back with that, but that's cool. So for all integers n, and then I want to negate this thing, right? And what is the key phrase here? I got an and. So that becomes an or, right? So such that n squared is not even, so that could be odd. Or, you see where I'm going here? And then what's the or n is even, which is the opposite of n is odd. This is tricky, just takes a little practice. It's like a new kind, it's like math, right? It's just some rules and you just apply the rules in the right way and you're done. Cool. Alrighty, let's actually do some proving some stuff now. So let me show you how we're gonna implement this to prove things that maybe are tricky to prove directly. And I'm not gonna ask you to do a whole lot of this. Probably for whatever our next exam is, I'll give you some take-home thing or something like that, where you get to write up a little proof about it. I'm not even quite sure that's gonna happen. So let's talk about proof by contradiction. This is that tricky, kind of a hack way to prove things. It's like a cheat code, like I said. I thought you were asking something there, you just like saluted me or something like that. All right, nice. So, to show a statement, P of X is true, we can assume it's false and show that that leads to some kind of contradiction. That's the whole method. We can assume P of X is false and show that that ends up proving like 2 equals 3 or something like that. It's false, and show this leads to a contradictory statement. That's the whole game. You might think, well, that sounds maybe complicated. Sometimes it can be. Sometimes finding the contradiction is the hard part. But it won't be for us. We're going to have like nice kind of forward, right in our face ones, which might not be apparent for a while. So let me show you how this is going to work. Let's prove the following statement. Let X be a rational number and let Y be an irrational number. And we'll talk about what that means just in a second here. We need to make sure we understand everything in our statement before we even start to try to prove it. Then, let's see here. Prove, how about we just say this, do this. Prove X plus Y is irrational. So the sum of a rational thing and an irrational thing is irrational. Let's get the definitions up that we need. In some ways, today's kind of one of our heavier days. So lots of new theory, ideas, putting it all together. So let's get some definitions up here. A number, a real number, X, is rational if, can somebody help me out with that? What is the definition? We talked about this a little bit. And you might just know it from before this class. What is a rational number?
A number that's not positive or whole.
Ooh, wait, say that again.
A number that's not whole.
Yeah, in a very precise way. That's totally right. Yeah, a number that's not whole, but what form does the number have? So, this is the key here. Ratio, what's a ratio?
Fraction.
A fraction, that's it. So it's a number that's a fraction. That's what this means. So a number, X, is rational, and so you were right.
Yeah.
It's just, these other ones are also not whole things, so we gotta be precise here. If X is equal to A over B, where A and B are integers, and what else has to be true to be safe? What has to be true about B?
Can equal 0.
Can't equal 0, can't divide by 0, and B is not equal to 0. So, in other words, just fractions. Like Joey said, they're just fractions. Yeah. What is an irrational number? This will be interesting. A real number, X, is irrational if, and you don't have to go too far. What do we think the definition of this might be?
It's not a real number.
Well, that would be pretty wild. Yeah, that would be. We're not going there, Joey. That is a place a person could go, but we're not going there. What do you think?
They're all irrational.
Yeah. What? Yes.
Oh no.
Oh, okay. Oh no.
Oh yeah.
Whole number? So that's
Fraction.
yeah. So check this out. All the whole numbers are actually still rational numbers because I can write 17 as a fraction. So that's, I like that we're thinking here. Yeah.
Wait, if it's a number over 0.
Yeah,
So
that would just be,
divided
that
by
would just
0,
be like
right?
an insane number.
Well, no, because it's not a real number at all.
Well, these are still real numbers, yeah.
Okay, well,
They're
I
still
get
real
it.
numbers.
It's partial.
I think you're thinking too deep
I
here.
think I am.
It's just not rational. So an irrational number is a number that's not rational if x is not rational.
So it can't be a fraction.
Can't be written as a fraction, i.e. x can't be,
Like pi.
yeah, there you go,
There you go, yeah,
as
pi.
a fraction.
Pi's irrational and real, right?
That is correct, sir.
Sick.
Look at this, man, it's a spouting wisdom over here. So let's get some examples. So pi, I like it. I'm gonna prove, I can't prove to you, proving that pi can't be written as a fraction is very complicated, we won't do it. But we will prove this one can't be written as a fraction, and this is one of the oldest proofs known to humankind, that this number can't be written as a fraction. And we're gonna use proof by contradiction for it in a bit. But most square roots, square root of 3, here's an interesting thing. Do you know this number? My calc friends know this number. That's E. Yeah, you can just say, what is that number? You just say E. Of course it's E.
It's a letter.
And then you just say, yeah, well, it's E, right? And it is. It's an irrational number that is very useful in calculus and business. We've probably got some business people in here. Have you ever seen this formula for compound interest? Principal times e to the RT. Anybody ever seen that business? Seen that, Kyle? Yeah. Yeah. That's for compound interest, continually compounded. Okay. We don't know that. That's okay. We don't know that. So this number is irrational. This is Euler's number. And I think we don't, like, here's some cool, interesting questions. Are these irrational? I don't know. I think they are. I think one of them we might not know the answer to. Yes?
What about infinity? Is infinity?
So infinity isn't really a number. It's more of like not for us anyway.
Okay, so you would consider that.
You would consider it an extended real number.
Extended real.
An extended real number. So we take the real numbers, and then we union in this symbol called infinity and set up some rules. And so it could be, but it wouldn't be irrational. It'd just be like its own thing. It's infinity. That's enough. You don't have to be more than anything once you're infinity. So this whole idea really blew the Greeks' minds. The Greeks, the very first textbook ever written was Euclid's Elements, and it was a book of geometry proofs. And in Greek thought, everything needed to be the ratio of two whole quantities. They thought that the whole world had to be this way, that everything was a perfect fraction if you just got the right fraction. And then Pythagoras came along. We know this name, yeah? Pythagoras came along and was looking at triangles. I think that Danielle is getting to hear this story again for the second time. And what is the relationship between the sides of this right triangle?
A squared plus b squared equals c squared.
Solid, yeah. So the Pythagorean theorem. And Pythagoras discovered this, or it was some other people kind of developed this theorem, but then started wondering, well, wait a minute, what if I have a triangle that has side 1, then that means, let's see, so here this is a squared is 1, b squared is 1, and that's c squared. So c squared is 2, and this really blew their minds because I needed a number that was essentially the square root of 2, and they couldn't find it. They couldn't figure out what it would be because it's not a fraction, and they spent a long time trying to prove that this was a fraction. And then a proof came along that you're going to see today that showed, no, this can't be written as a fraction. And that caused a lot of trouble. Every time a new number comes along, I think I've said this before, somebody dies, right? So you don't create a new number. if you want to live a long and healthy life. So, just like the whole history of math is filled with things like this. We got our definitions. Let's go back to our problem. It's easy to get off on rants and tangents in here.
Is that a threat?
What's that?
Making a new number thing?
Yeah.
I'll kick up in my house. Erase
You're gonna go use your check to publish your paper.
Publish it.
All right.
11T.
So, okay, so what we're gonna do is proceed by proof by contradiction. So let me show how this goes. So proof. So we're gonna assume that x is rational and y is irrational, but that their sum is not irrational, which means it's rational. So assume x is rational, y is irrational. And this is kind of like, this is like the if, and then this is the then part. So I'm assuming that this is true, but the light is off. So what is the opposite of this? How can I say the opposite of this? And x plus y is not irrational. What does it mean to be not irrational in simpler terms, i.e.? So what does it mean to be not irrational? What are you? Rational, yeah, exactly. So you're either, every number is rational or irrational. You either can be written as a fraction or you can't. So there's two classes of numbers, i.e. assume that x plus y is rational. Okay, so now we've got handles. And let's think about this thing to begin with. Like when I come back and I'm thinking about this statement, I've got x is a fraction, y is not a fraction, and I want to prove this is not a fraction. How do you prove something isn't a fraction? Like that's a really hard thing to get your head around. So if we approach this way, we've got two handles. What are the handles? Look, this is a fraction. And now this is a fraction. So now I've got two things that I know are fractions. I've got two things I can write a formula for. There's no formula for when you're irrational. It's just, if you're irrational, it's, well, I just can't be written like that. That leaves open a whole lot of stuff. So, all right, so we got our assumptions.
Wait, how?
Yeah,
That's
go ahead,
really
Joey.
confusing.
What's that?
So, because one of the numbers is irrational and one of them is rational, the entire thing is rational?
Well, this is, I'm sorry, I should have said this. Proceed by, we're gonna use proof by contradiction. Sorry, thanks, Joey. So this makes this, use proof by contradiction, i.e. assume. So we're gonna assume this is true, but this is false.
Okay,
So that, and then we're gonna show that we got a contradiction somehow.
okay.
Does that make sense? A little clearer?
Yeah.
Yeah, thanks for saying that.
Yeah,
So
I was a
proceed
little-
by proof by contradiction. Assume that, and assume this is false. In other words, that x plus y is rational. So let's get some stuff that we know. Since x is rational, what can I say? X is what?
Real numbers.
It's a real number, but what does it mean to be rational?
Fraction.
It's a fraction. Cool. So I write that out. So we'll say x is equal to a over b for some integers a and b. And b is not 0. Awesome. What else do I have a handle for? So I've got y is irrational. I don't know what to do for that, but what else could I write up here? Also, what else do I have? Yeah, x plus y is rational. Yeah, also x plus y is rational. Now, this is the opposite of what we're trying to actually show up there, but we know that this is the opposite, because we're going by contradiction. So you gotta keep in mind, and I'm super glad Joey asked me about that, because I am proceeding by contradiction, so this is gonna blow things up for us. I.e., that x plus y is some other fraction. You gotta use different variables. We don't know that they're the same for some integers, x, c and d is not equal to 0. Okay, so now look at what we've got. Let's put these things together and see if we can fit them into a spot in our mind. So we've got x is a fraction. I've got x plus y is a fraction. What can I do to figure out something about y? So now I need some information about y. What could I do here?
Y is not a fraction.
Well, we do know that. So we already know y is not a fraction, right? We're definitely assuming that. We know y is not a fraction. But how can I relate it to these fractions here? How can I relate it to something that says it's a fraction? How could I show that these two things mean y is a fraction? Yeah, plug x in. Like, it's not super deep. So take these two. It's not too bad. You're never quite sure where to go until you see where to go. But plug x equals a over b into x plus y equals c over d. Now, we're trying to find a contradiction here, and we're just about to see it. To get, and so I plug that in, I get a over b plus y equals c over d. So what is y equal to? Just don't think deep. Just
C over d minus a over
beautiful.
b.
How do I add those two fractions?
Just subtract.
Just subtract it. Yeah, how do I subtract two fractions? That's beautiful. You're absolutely right.
Get a common denominator.
Common denominator. What's the denominator I should use here? BD. Beautiful. So I'm going to multiply this one by b over b and this one by d over d. So here we're going to get common denominator. And so this is going to be c times b over d times b minus a times d over b times d. And then I put them together. And this is CB minus AD over DB or BD, whatever you want. All righty, where's my contradiction? So where's the contradiction? So now you kind of got to be watching the ball, right? What is this top? Is this top an integer? So is CB minus AD an integer? Let's start there. And why?
No, because you can't subtract.
Oh, but you can, can't you, right? If I take two integers and I subtract them, still get an integer. But you're on the right track here. Let's start off. C and B are each integers.
Yes.
So is C times B an integer?
Yeah.
Yes.
Yeah, and we just said that, right? Because they're closed under multiplication. That's in everybody's proof. A times D, is that an integer?
Yes.
Yeah, because A and D are both integers. So the difference of two integers is still an integer, yeah? So the integers are closed under multiplication and subtraction. So this top is an integer. So this is an integer. And this is an integer. So what is y? Y is equal to an integer over an integer. What do you call that? A fraction, what do you call that in fancy terms?
Rational.
Rational, yes. So this means, i.e., y must be rational. What am I contradicting? Where's the contradiction?
That y is irrational in the assumption.
Totally. Yes. So yes, that's it exactly. Nice, Vincent. So we've got this. We've got, we assumed x is rational and y is irrational. And then we assumed x plus y is also rational. And if that's the case, then that means y must be rational, but that's a contradiction. So this is a contradiction. What caused that contradiction? Assuming that this is true. Thus, x plus y can't be rational. Because if it is, I can do all that shit. So x plus y must be irrational. Right. That's a pretty sloppy proof. That's all over the place. Try to get a little cleaner one on the next one. Is that an applause?
Yeah, like,
Oh,
yeah,
thank you.
I think you deserve one.
Oh, indeed. Thank you, sir.
That was, yeah.
You like mine?
I'm still like, why did we assume that x plus y is rational? 'Cause
Okay.
that to me doesn't make any sense, because if x is rational and y is irrational, you can't add them together and have it be rational.
Well, you're right. That's what. So let's start
So
beginning.
why
So-
couldn't I just say that? Like, isn't that easier? Like,
Well, because like you're just saying, because you're basically just saying stuff. Like, how do you know, Joe?
Because if you can't write something as a fraction, you can't add it to another fraction and have it be rational.
How do you know? You're just
Like-
saying stuff. Though.
Oh.
You're just saying stuff. How do you
Just
know?
proved it.
How do you know that I can't add some fraction to pi that makes this rational? How do you know that? It
I guess
feels
I
right.
don't,
You're
but,
just
like,
like
it
going
just
off
feels
feelings,
wrong,
right?
though.
Like, so you're using intuition. That's awesome. Your intuition is spot on.
But it's right intuition.
Yeah.
Right? Okay.
Yeah, exactly. That's what's spot
Okay,
on.
But you just have to prove it using that.
Correct.
Okay. Yeah,
Yes,
yeah,
we
yeah.
have to have a logical flow that
I guess
demonstrates.
I just would have never I never would have thought to assume that x plus y is rational. Like, I just would have started doing the proof after writing assume.
So
x is
let's
rational,
talk
y is
about why you
irrational.
can't go direct. So I like that you're engaged with this and it's pissing you off.
It is. It's like.
No, that's wonderful.
Ugh.
That's awesome. So let's try to prove this directly. Let's see what happens. So x is rational. So let's just, no contradiction, right? So actually go to the, yeah, that's it there. So x is rational, so I can do that, right? Y is irrational. What do I say about y?
It can't be written as a fraction.
Yeah, so it's not equal to any c over d for any integer c or d. So I'll just use some fancy notation here. Any integer c or d. Show that x plus y is not equal to any fraction. So how do you make that solid? That's the part that starts to hurt when you try to do it. What's great about the other approach with contradiction is I'm saying, see, this whole not equal to any fraction is too big. Like, what does that mean? Oh man, did I have to think about every fraction in the world? But if we say, well, wait a minute, what would it mean if this was a fraction? Oh, then it's really clear that if x is a fraction and this is a fraction, then y has to be a
Okay.
fraction.
No, I get it now.
See?
It's because you can prove that. You can assume that y is rational and prove that y is rational, but you can't prove that it's irrational. So by proving that it's rational and saying that it's already irrational in the beginning, then you're contradicting it and proving it.
Joey.
Okay, I understand.
Joey. Yeah, that's great, man. That's awesome. You have no idea how happy this is making me. Seriously. Is there any other questions on it or challenges to the method of proof by contradiction? Because that's fucking great.
Trial by fire.
Trial by fire. Let's do one that maybe feels a little bit more down to earth and isn't all about rationals and irrationals, because that's a little nebulous and very abstract. You like this one. All right. So prove that if n squared is even, then n is even. This looks a lot like stuff from the last exam, kind of, right? Like multiple of 2 stuff, divisible by 2. let's think about how hard this would be to go directly with. So if I wanted to prove this directly, and this is going to be painful, and we're not going to do it, but I would have to assume n squared is even. So what would that mean about n squared? N squared is what? What does it mean to be even?
Equal to 2k.
2k for some k. That's an integer. Yeah. Nice. Okay. Now how do I get information about n? Because now I need to show n is also, but I just know n squared. Where do we go? Well, I could take the square root. I take the square root of both sides, the positive square root, I get this. Oh shit. That looks really irrational, right? That doesn't look good. So this direct approach just sucks. Like, because you end up here and you just don't have anywhere to go. But what if we go by contradiction? So let's proceed by contradiction. Proof. Use contradiction. So what is the negation of this? I.e., so, and yes, assume the switch is on. What else? What is the opposite? Switch is on, but the light is off. So switch is on, so n squared is even, and n is odd, yeah. Okay. Now I've got formulas. The great thing now is, okay, now I've got a formula for n, and I just need to see if that is consistent with n squared being even. So let's write this out now. Since n is odd, n is equal to, did we talk about how to write odd things? I think we know we talked about even. Yvonne nailed that. What does it mean to be odd? Oh, yeah,
It's like 2k plus 1.
Beautiful, so good. So n is equal to, let's use L because I already popped a K. Oh no, we didn't pop a K on this one. So we got that. We like that, pop a K. Okay, anyway. So for some integer K. Nice. So check this out, now let's square n. Then n squared is 2k plus 1 squared. How do I multiply that all out? Foil it out. I love it. You're on fire today, Joey. But that, man, we just gotta get you paid every day, and it like brings you in a new man. So first times first is 4k squared. The outer is 2k. The inner is 2k. The last is 1. So this is 4k squared plus 4k plus 1. Beauty. Does that look even? Because we're assuming that n squared is also even. What? I hear things murmur. I hear like brooks babbling in the distance. Sometimes that sounds like you're camping and you're by a stream and you hear voices in the stream late at night. Oh no, maybe we shouldn't talk about that.
Okay.
So,
Some people just don't get it.
you know what I'm talking about. Yeah. It's like, what? Somebody's sneaking up on me. Maybe you have to be paranoid or.
Fire a couple of shots in the darkness.
That's shooting the creek, yeah. Is this even or odd?
It looks odd.
Why does it look odd?
Because you got the plus 1.
Yeah, it does, right? It looks like it's twice something plus 1. And it is. So Yvonne's intuition is telling him this isn't, this is odd. And that would be right, so check it out. It's 2 times what plus 1? What goes in here?
2k squared plus 2k.
So lovely. Is this an integer?
Yes.
Yes, it is. Why?
This goes by multiplication and addition.
Oh, that sounded so good. Did everybody hear that? So since the integers are closed under multiplication and addition, this is an integer. Let's write this shit up and make a beautiful proof as opposed to my slop that I had on the last one. So, making this nice and pretty. So n squared. Since the integers are closed, just what Yvonne said, under multiplication and addition. 2k squared plus 2k is an integer, because k is an integer. So n squared is equal to 2l plus 1, where l is this thing, is an integer. Where's my contradiction?
That would make 2l or 2n squared odd instead of even.
Yeah, so that makes n squared odd, but we're assuming that n squared is even. So that collides with the fact. This means n squared is odd, contradicting the assumption that n squared is even. Thus, n squared must be odd. Oh, wait, whoa, what are we saying? Oh, thus n must be even. Sorry, this is the thing I changed here. That's right here. So, thus, n must be even. Because this was the thing we changed. We changed this to odd. And changing that is what made all this happen. And that's what made it look like n squared is odd, so that's a lie. So n must be even. That's the end of that proof. It's tricky. It's tricky stuff, but it's like the only way you can proceed sometimes. Sometimes it's the only way to go. Let's just do one together, real quick, and then call it a day. Or why don't we just call it a day now? Does that sound all right?
Oh.
No?
Yeah.
Yes.
Yeah.
That was how nice of you, girl. Not a no. Come on, girl.
Is this okay? We call it right now? Wait, are you sad? Wait, I feel like some people are sad now.
No, I think it's okay. I think Joey's just sad because he's not here.
Well, Joey's gonna stay.
Oh, nice.
Yeah, no, Joey will be staying with me and working on this. You can hear it. Yeah, we got a break, so everybody knows we don't meet on Monday.
Yeah.
Everybody knows that, right? We don't meet on Monday. I'll email you tomorrow. I'll have a few things for you to look at with this. Not much. I want you to have a good break, so I'm not going to give you a bunch of stuff to do. So just a little bit. Yes, sir.
Look at this real quick.
Yeah. Hold on a second. What is that?
That is rhetoric.
Oh, okay.
Is
Yeah,
there,
we can take a look at that. Hold on. Let me give you your corrections back.
is there a connect due tonight?
There was like a prep. Yeah, there is a. Wait, wasn't it due yesterday, or was it due today? I don't even know. Somebody help me out.
The prep was due at 12:15. The actual homework's due tonight.
Okay. Do we need any more time on any of that?
I mean,
I think I'll be fine.
What's that, Yvonne?
I think I'll be fine.
You think you'll be fine? You're good? Okay, all right. Yeah, let me get these exams. Where the hell are they? Okay, so some folks followed my directions quite well. I'm very grateful for them, and I said so on there. I think. Did I get one of these from you, Daniel? Good. Some folks did not follow the instructions even remotely. Even remotely. So, if you didn't do what I asked, and you clearly didn't read those instructions, you probably didn't get all your points back. That's a lot of folks in here, honestly. That's a lot of us here. All right, let's see. Where is Alex? Mr. Alex. Oh, he's not even here. There's Mr. Ilan. Thank you. The next page, or Abraham.
Do you want me to stop recording?
Thanks. That would